The global refined tin market has entered a severe structural deficit, projected to reach 24.5 kilotons in 2024. This supply gap represents a 155% expansion compared to the previous year. The imbalance is driven by contracting global production, which fell 3.3% to 358.0 kilotons. Meanwhile, inelastic demand from the electronics sector pushed global consumption up to 382.5 kilotons. This physical mismatch has forced London Metal Exchange cash prices to rebound to an average of $32,100 per metric ton. The price escalation reflects a market stripped of its operational buffers. Exchange inventories have depleted to critical operational thresholds. London Metal Exchange warehouse stocks fell 62.3% from their January peak to just 2,900 metric tons by October. This volume represents less than 3 days of global consumption, leaving the supply chain highly exposed to disruptions. The primary catalyst for this drawdown was an administrative bottleneck in Indonesia, the world's largest exporter of refined tin. Regulatory restructuring and licensing delays caused Indonesian exports to collapse by 80% in the first quarter of 2024. Consequently, spot prices surged 29.6% in a 90-day window. Advanced computing and automotive electrification are compounding this structural deficit. Tin solder demand within artificial intelligence and high-performance computing is growing at a compound annual rate of 27.4%. This growth is driven by high-density packaging and complex multi-chip module architectures. Simultaneously, the proliferation of electronic control units in electric vehicles will push automotive tin consumption to 39.5 kilotons by 2025. Because standard lead-free solder has no viable chemical substitutes, these sectors are highly price inelastic. A 30% increase in raw tin prices inflates the total bill of materials cost for advanced circuit board assembly by up to 15%. The Chlor-Alkali process is highly energy-intensive. Electricity represents up to 70% of variable operating costs for these electrochemical plants. When European wholesale electricity prices surged to an average of €450 per megawatt-hour in late 2022, operators were forced to curtail production. Capacity utilization fell to a historic low of 58%. Because chlorine gas is highly toxic and cannot be stored in large volumes, these curtailments immediately restricted the synthesis of downstream hydrochloric acid. Even as energy prices stabilized near €110 by late 2024, regional capacity utilization remained structurally suppressed at 73%. The contraction of primary electrochemical capacity triggered a severe regional deficit in hydrochloric acid. European industrial-grade spot prices surged by 180% in 2022. This price shock rapidly cascaded into advanced manufacturing sectors. For semiconductor fabrication, ultra-high-purity hydrochloric acid is an irreplaceable agent for wafer cleaning and gas phase etching. European lead times for this critical chemical extended from 4 weeks to a peak of 16 weeks. In contrast, United States lead times remained stable between 3 to 5 weeks, highlighting the highly localized nature of the European bottleneck. To prevent catastrophic fabrication shutdowns, European semiconductor manufacturers restructured their supply chains. Domestic European production of semiconductor-grade acid fell from a 75% market share in 2021 to 45% in 2022. Fabs doubled their reliance on United States imports to bridge the gap. By 2024, foreign imports from the United States and East Asia retained a structurally higher market share of 48%. This shift represents a permanent diversification of the supply chain. Localized energy shocks have structurally reduced European chemical self-sufficiency in favor of international logistics lines. Aerospace-grade carbon fiber production is constrained by a highly concentrated upstream chemical process. 3 Japanese conglomerates control 74.2% of global polyacrylonitrile precursor capacity. This concentration creates a single point of failure for Western defense supply chains. The synthesis of this precursor requires extreme chemical precision. Acrylonitrile monomer must be polymerized with specific comonomers to keep the molecular weight distribution below 2.0. Any deviation introduces microscopic voids, causing catastrophic structural failure under aerodynamic loads. The market has transitioned from a pre-pandemic surplus to a severe structural deficit. In 2024, global demand for Precursor reached 70,200 metric tons. This exceeded nominal capacity by 4,200 metric tons. This deficit is driven by a dual demand surge. Defense demand grew at an 8.7% compound annual rate, while commercial aviation rebounded rapidly. Furthermore, the conversion process requires 2.1 kilograms of precursor to yield just 1 kilogram of carbon fiber, compounding the raw material deficit. The structural deficit has severely impacted downstream defense procurement. Lead times for high-modulus carbon fiber escalated from 18 weeks to 62 weeks by late 2024. This delay directly impacts tactical missile and stealth airframe assembly schedules. Concurrently, average spot prices rose 97.8% to $89 per kilogram. Relieving this bottleneck is highly capital-intensive. A new domestic precursor line requires up to $500 million and 3 to 5 years for aerospace qualification, preventing any rapid market correction. The Western supply chain for orbital propulsion has collapsed into a single-source vulnerability. Regulatory tightening in Europe and the United States has forced the closure of key manufacturing plants. Only one qualified facility remains active in the West, located in Lake Charles, Louisiana. This consolidation has triggered a severe price escalation. Spot prices for Aerospace-Grade and Hydrazine rose 275% over the last decade, reaching $450 per kilogram. New environmental risk management rules implemented in 2024 have added up to 22% in recurring compliance overhead. Commercial space operators have largely bypassed this chemical bottleneck by transitioning to electric propulsion. Electric systems captured 62% of the satellite market by 2024. These systems utilize inert noble gases like krypton and argon, avoiding toxic chemical handling. However, national security architectures cannot rely solely on low-thrust electric systems. Hydrazine remains non-substitutable for high-thrust, rapid maneuver missions that require instantaneous velocity changes. Green monopropellant alternatives remain constrained at 7% market share due to high catalyst costs and slow qualification timelines. This leaves critical defense payloads tethered to a fragile, single-source chemical supply line. The Welland Canal is a critical mechanical bottleneck bypassing Niagara Falls. It handles an average of 32.8 million metric tons of cargo annually. Agricultural exports, primarily wheat and corn, represent over 30% of this volume. Metallurgical inputs like iron ore and coal feed the integrated steel mills of the southern Great Lakes Basin. This specialized maritime corridor has no immediate deep draft alternative. The infrastructure is operating far beyond its original 1932 design life. Annual maintenance expenditures rose 81.3% to $118.2 million Canadian dollars in 2023. Yet, unscheduled lock delays quadrupled over the same period, reaching 168 hours. Structural concrete delamination and mechanical fatigue at locks 7 and 8 drive this operational decline. The system is requiring exponentially more capital to arrest physical deterioration. Land-based transport cannot easily substitute for this marine corridor. Rerouting bulk commodities to Class I rail networks imposes an average cost premium of 153.5%. For iron ore, the penalty is a 160.1% increase, directly threatening steel manufacturing margins. Absorbing a complete canal closure would require 12,000 additional railcars per week. This volume would instantly overwhelm regional rail networks, driving up inland freight rates across North America. Environmental mandates are restructuring global cold chain logistics, creating a severe manufacturing bottleneck. The transition from high global warming potential hydrofluorocarbons to carbon dioxide systems has extended refrigerated container lead times. Average reefer delivery times surged from 6.5 weeks in 2018 to 28 weeks in 2022. This delay is driven by the adoption of R744 natural refrigerant systems, which reached 31.5% market penetration in 2024. These systems operate under transcritical conditions, requiring highly specialized scroll compressors. Manufacturing these units requires 3.5 times more machining hours than legacy hardware, capping production velocity. The bottleneck is fundamentally thermodynamic. Carbon dioxide systems operate at 1,740 pounds per square inch, an 8-fold pressure increase over legacy systems. This extreme pressure shifts manufacturing requirements from standard sheet metal to heavy-duty, thick-walled cast iron scroll compressors. Consequently, Production is highly consolidated, with 3 firms controlling 88% of the global market. These suppliers face severe metallurgical constraints in casting high-tensile strength compressor shells. Current global output is capped at 65% of annualized replacement demand, preventing rapid supply-side scaling. This equipment deficit has triggered severe downstream economic consequences. The spot rate premium for refrigerated containers on the South America to United States East Coast corridor remains elevated at $4,800. Globally, average reefer spot rates have stabilized at $6,900, a 115% structural increase over pre-pandemic baselines. These elevated costs are compounded by worsening operational risks. Extended equipment, turnaround times, and compressor repair backlogs have disrupted critical agricultural trade lanes. Average transit-to-destination spoilage rates for high-value fruit have increased by 4.2 percentage points since 2021. The regulatory transition has compromised cold chain reliability. Urban power grids are reaching their physical limits. Data center clustering and electrification are driving unprecedented load growth in space-constrained metropolitan areas. High-temperature superconducting cables utilizing second-generation rare earth barium copper oxide tapes offer a high-density alternative. At a normalized 138 kilovolts, a triaxial superconducting cable transmits 1,000 megawatts of power. This matches the capacity of multiple conventional circuits while reducing the physical footprint by 64%. The resulting power density is 18.4 times higher than conventional copper cables. This spatial efficiency allows utilities to retrofit existing 100mm underground ducts. By avoiding new civil excavation, operators bypass the primary cost driver of urban grid expansion. Civil works typically account for 55 to 70% of total project expenditures. The primary bottleneck for superconducting transmission is not the physics of the cable, but the reliability of the cooling system. Superconductors require continuous cryogenic cooling at approximately 77 Kelvin. The mechanical refrigeration units, or cryocoolers, have historically exhibited low mean time between failures. Average cryocooler reliability has improved from 12,000 hours in 2015 to 44,000 hours in 2025. This progress narrows the gap to the 50,000-hour utility reliability threshold. However, any cooling failure triggers an instantaneous thermal quench. During a quench, the cable transitions to a highly resistive state within 50 milliseconds, risking catastrophic thermal damage. To mitigate this risk, 92% of active installations deploy redundant cooling configurations. This mechanical redundancy inflates initial cryogenic subsystem capital costs by 45 to 80%. Economics of superconducting grid projects are shifting. While the cost of the superconducting wire itself has declined by 33% since 2018, cryogenic cooling costs are rising. The cooling subsystem now accounts for 27% of total project capital expenditure. This cost inflation is driven by the integration of high-reliability helium and nitrogen compressors. Operational logistics also present a front-loaded hurdle. Initial cool-down protocols require up to 15,000 liters of liquid nitrogen per kilometer of cable to reach operating temperatures. Consequently, these systems remain restricted to high-density urban corridors. The high capital cost of cryogenic infrastructure is only justified where conventional right-of-way acquisition exceeds $15 million per kilometer. Cryogenic engineering, rather than material science, remains the gating factor for next-generation urban grids. Russia's strategic ambition to establish a year-round Northern Sea route is failing to meet state-mandated cargo targets. The 2024 federal target of 80 million metric tons faces a 52.5% deficit, with actual volumes flatlining at 38 million tons. This divergence is driven by Western sanctions on the Arctic LNG 2 project and a critical shortage of specialized ice-class cargo vessels. By 2030, the target of 220 million tons will fall short by over 125 million tons. The underlying constraint is physical. The active nuclear icebreaker fleet is projected to plateau at 8 to 9 vessels, far below the 12-hull minimum required for continuous multi-lane escort operations. Domestic shipyards cannot rapidly substitute Western marine technologies. The flagship 120-megawatt icebreaker, Rossiya, has slipped from 2027 to 2030. This 3-year delay stems from metallurgical casting defects in the massive propeller shaft brackets and steam turbine housings. Smaller 60-megawatt project, 22,220 vessels, face an average delay of 2.1 years. Attempting to substitute import-dependent components with domestic alternatives, such as Kirovsky-Zavod turbine generators, has crippled production schedules. Furthermore, the retirement of legacy Soviet-era icebreakers by 2028 will offset new commissions, yielding a net gain of only 2 active hulls over the next 4 years. The icebreaker deficit destroys the geographic advantage of the Arctic corridor. Without active escorts during the winter freeze, specialized ARC-7 carriers must slow to 3 to 5 knots. This extends transit times to 52 days, which is 17 days longer than the traditional Suez Canal route. Operating without escorts increases the hull requirement ratio to 1.5. This means energy projects require 50% more highly specialized, capital-intensive vessels to move the same annual volume. Rerouting cargoes around the Cape of Good Hope to bypass the ice blocks extends the round trip to 90 days, adding $1.4 million in fuel costs per voyage.